Even our own Milky Way is dominated by dark matter. There's the rotation curve. This is an old plot. I should probably find a new one, but it gets across the point. There's the rotation curve of our own galaxy. The velocity of rotation rises pretty rapidly, and then it kind of spreads out here. I think the actual number for the sun now is up a little higher than this, maybe more like 250. But the point is, it's flat. Okay, we got a flat rotation curve to well beyond. I mean, look at how far out this goes. Now you might be saying, but Rick, you told us the sun was about 2/3, 3/4 of the way out to the edge. How could you possibly measure stars way out here? There aren't any stars, Rick. And yeah, okay. So what we do is we take advantage of the fact that there's also cold hydrogen gas in the disk of our galaxy. Remember, that's how you make stars, is out of cold gas. And that gas goes out much further than the stars. And that gas turns out to have a spectral line in the radio part of the spectrum. The 21 centimeter line, it's due to a spin flip in the electron. It's something I don't really want to go into, but you can look it up, spin flip radiation. It's a nice convenient way to see, quote unquote, cold hydrogen. And so we can measure the wavelength of that and then get the velocity of that gas going around in a circle around our galaxy. And there it is. It doesn't go down to well beyond the position of the sun. So we are surrounded by a dark matter halo. Our galaxy is inside of a huge halo of dark matter. In some ways I like this graph, but in other ways I don't, because it looks like the dark matter just sharply cuts off here. And it doesn't. What it does is it's denser in here, and then it gets less and less and less as you go out, and less as you go out. So the shading could have been done better, and if I look through Google, or maybe you guys could Google and try and find me a better image, but I really like otherwise the way it shows the disk, it shows the bulge, and it even shows the globular clusters in the inner halo of our galaxy. But there's an outer halo that's not full of anything except dark matter that just goes on and on and on. Probably halfway to Andromeda. Okay, so now we get the fun part. So how do we figure out what the dark matter is? So when you're doing science, again, you want to obey Occam's razor, not just because Occam said so, but because you also have scarce resources of money, of graduate student time, and frankly your own career time, and also a little bit of urgency in racing to get the answer before somebody else scoops you on the great discoveries. And so you try to guess the right answer first. So you start with the stuff that could be easily tested and which you already know exists. Okay, so what could the dark matter be? So what we want to do, I mean, normally if we were in the classroom, I'd literally be asking you, and I would hope you guys would come up with ideas like, well, Rick, could it be this? Could it be that? Could it be... And not go out into the wild blue yonder. Okay, we don't want to go to the wild blue yonder of blue flashing lights. Not yet. Okay, because that's what makes it fun. We don't go out there yet. Could it be gas? Could it be just plain old hydrogen gas? We know that hydrogen is 90% of all the atoms in the universe. Maybe there's just a lot we can't see. In fact, Rick, you've already just told us that there's cold hydrogen out there. Maybe it's just cold hydrogen gas. No, it can't be cold hydrogen gas. And here's the way you test that. You look at other galaxies that are past the dark matter halo. You take advantage of the fact that we have to look through the dark matter halo that we live in to see other galaxies beyond our own. So you can look at the Large Magellanic Cloud, which has some nice bright nearby stars. That's a good way to do it. Or you could look at more distant things if you want. But the LMC is plenty far enough away that it samples the large majority of the dark matter of our galaxies, near as we can tell. And you look for what? Absorption lines of hydrogen. You look for H alpha in absorption, H beta, H gamma. Or if you really don't think it's hydrogen, you could look for helium lines. Probably hydrogen, though, is the natural thing to look for. It's what the stars are made out of. The stars just formed out of gravity, out of the available stuff. If that's what you're saying the dark matter is the available stuff, it's almost certainly got to be hydrogen. Well, we look, and no, there's no absorption lines. I mean, there's a little teeny bit, okay? So we did say there's some cold hydrogen out there in the disk of our galaxy, but there's nowhere near enough to account for, roughly 90% of the mass of our galaxy, which is what we need. Could it be dust? So here's a dust cloud hiding background light. So how would you tell if you're looking through dust? And we talked about that. And we saw, and maybe you can even see in this slide a little bit, how the stars that are partially hidden in the dust are actually, well, I don't really know where this slide came from. I'm starting to wonder whether somebody just created it ad hoc. I think maybe there really is dust here. Can you tell how the stars are a little redder here? Now that star's red for a totally different reason. That's probably a red giant. But when you look at stars through a dust cloud, then it will scatter out preferentially the blue light. And it's the same phenomenon you see every sunrise and sunset. The sun looks redder because you have to look through dust, aerosols, smog, exhaust, sea salt crystals, whatever. Aerosols typically have wavelengths that are of order a few times, or maybe even less, of the wavelength of visible light. And that's true also of interstellar dust. It has a wavelength, it has a size that's of order a micron or so, and that means that it's about twice the wavelength of green light, about 3 times the wavelength of blue light, and that's sort of a nice preferential size so that it has a strong preference for scattering the blue light and not so strong for the red light. So you look for interstellar reddening. Dust would redden background starlight. So what you do is you look at other galaxies like Andromeda, maybe take a big patch of blue stars, bluish looking stars. You look at the spectrum, you say, I know what kind of spectrum that is. That's the spectrum of an A0 star. I see the collected light of all these stars averaging out to pretty much an A0 type spectrum, or an A5 or whatever. Okay, spectral types, we talked about those. And you say, well, I know what color an A0 star is. We see those in the night sky, and we know exactly what the color index is. And gee, the color index of this galaxy is a lot redder than that. So the spectrum temperature is hotter than the color temperature. I guess I must be looking through dust. That's how you test it. But there's no dust. Fails. So it's not dust. It's not gas, it's not dust. Okay? Well, could it be rocks? Small things, but a lot bigger than dust. Could it be asteroids? Could it be comets? No, and here's the reason for that. First of all, we do have to say that if they're rocks, asteroids, or comets, you would not be able to so easily directly rule them out as you could for dust and for gas. And the reason is because almost all of the atoms that make up rocks, asteroids, and comets is hidden beneath the surface of the rocks, asteroids, and comets, and therefore doesn't interact with light. So the interaction of each of these things with light, when they're this far away, is so tiny that you wouldn't be able to tell. They don't have enough gravity that you can use that. Frankly, that's another good test we're going to come to in a minute. But they're not small enough, not powdered up enough that they have enough surface area to interact with outside light to directly detect it. So you have to put on your thinking cap and do some indirect testing. And here's how the indirect testing goes. You realize that all of these things are held together by solid state forces. They're held together by the chemistry of heavy elements, or what we call in the business metals. Okay, they can't be made up of hydrogen and helium purely, because hydrogen and helium doesn't make rocks, asteroids, and comets. The large majority of the mass of each of these things is in heavy elements. So then we ask, well, wait a minute, there are stars out there. There's stars in the halo of our galaxy. We know what they're made of. We talked about that. They're POP2 stars. They're stars with no heavy elements. They're made up of almost pure, pristine hydrogen and helium that came right out of the Big Bang. But wait a minute, Rick, gravity works on everything. Gravity should pull together whatever's out there, including heavy elements. There's no reason that only the hydrogen and helium should glom together to make stars. I mean, if most of the matter of our galaxy is in metals, they ought to be most of the matter of the stars that are out there. And they're not. In fact, they're even a smaller percentage than what's in the disk, where there isn't so much dark matter. So it can't be rocks or asteroids or comets. So the same reasoning that rules out dust will tell you that there can't be basically giant dust gloms making these things out there either. Okay, well, what about heavier things? Things that are big enough to be self-gravitating. So we talked about how things need to be at least a half a mile across before they begin to have enough gravity that you can begin to notice it. And the bigger it is, the more gravity it will have. So gravity will affect things now in another way that allows us to test gravitational lensing. So now we're talking about anything, not just rocks and asteroids, but dead stars, dim stars, red dwarfs. We talked about how red dwarfs are most of the stars in the local neighborhood. They're almost certainly most of the stars in the whole galaxy. And if they're out there in the halo, they'd be way too dim for us to directly detect. Maybe they're just red dwarfs out there. Maybe they're dead stars. Maybe there's a whole population of massive stars that lived out there long ago and they all died, and now they're all just, their dead corpses are floating through the halo of our galaxy, and they're too small and too dim. Remember, white dwarfs are only the size of the Earth. Maybe it's white dwarfs. Maybe it's black holes. You know, you can even get more exotic black holes all the way down to, smaller sizes than you could account for by the deaths of stars. Who knows how you make black holes? Maybe you could make them other ways. So we need a name for these. And the group of astronomers who decided to do the first big study on this, decided they would use their, I suppose, young and adolescent male thing and call them massive clustered halo objects, because they're in the halo of our galaxy. Machos. Okay, so their group came to be called, I suppose, with not a little bit of encouragement from themselves, the Macho Collaboration. So, the Macho Collaboration. And the idea here is that if a macho passes in front of a distant star, you will be able to tell. Now, you might first think that, oh yeah, I could figure out how that would happen. If it passes in front, we're going to see an eclipse, and the background star will disappear. So we could look for eclipses of stars in the large Magellanic Cloud or the small Magellanic Cloud, or maybe if we're careful enough, even all the way out to Andromeda. We could look for eclipses, but I would say no. If you do the math, you'll find out that for things that far away, for throws that are that long, now we're talking hundreds of thousands of light years, then it is not an eclipse that you would look for. Instead, the gravity of these things, no matter how weak, is actually enough to bend the light a little bit, enough that you'll actually get more light into your telescope and not less. So it was chosen, I think pretty naturally and obviously, to use the LMC, the Large Magellanic Cloud. LMC. There's a picture of the LMC. So yeah, there are a lot of dim stars that just turn into a blur, but there's a lot of bright stars here too. And so what they did is said, here's what we're going to do. We're going to ask for a ton of telescope time, but they're going to give it to us because we're going to discover what is the dark matter. Any dark matter that is self-gravitating, we're going to be able to find it. So they did the math, they did the statistics, they said, you know, if there are dead stars out there and they have roughly a solar mass, and we know that the mass of the galaxy from what we've measured is about 1 trillion solar masses, and if most of that's dark matter, then how many machos is there, and how fast are they moving, and therefore how often should we see them pass in front of a star, and let's just get as many stars as we can on our CCD chip, and how often do we have to take a picture. And they worked out the numbers, and it turns out that, gee, you know, we could do this. This is doable. If we just take a picture, a couple of pictures a night of the LMC every night for a few years, we ought to see hundreds and hundreds of macho events as a macho goes directly in front of one of these stars. And what you would expect to see is that star to brighten. Now, the next question, though, you'd want to ask is, well, how long should the macho cause the brightening? Because if it happens in an instant, we're going to need to take like a video, and we don't have the hard disk space to do that. I mean, we could take 2 or 3 pictures a night, but we can't stare at them nonstop. That's just too much. Well, you do the calculations and you realize, you know what? These things move slowly enough out there that they'll stay bright, extra bright, for about a day and a half, 2 days, 3 days, something like that. That's reasonable. That means you're not going to miss them. You'll catch them. I mean, assuming you have clear skies where you are. And so you work those numbers into your statistics, and they did put together a pretty good proposal, and time allocation committee said, yeah, this looks good, let's do it. I know this is a lot of time, but you know what? This is the most important problem in astronomy, bar none. So yes, and you guys are the right guys for the job. You guys get to find what is the dark matter. So here's a macho event. There's a distant star. Obviously, we're zoomed way, way, way in. You can see the little pixelation here. We're zoomed way in, and then it brightens up, and then it goes back to being normal again. Now, part of what you have to worry about is the following, though. You might be saying to yourself right now, gee, Rick, couldn't there be just plain old variable stars that are doing stuff like that? I mean, how do you really know it's a macho? All you're really seeing is a star that gets brighter and then dimmer. So you think about, well, what kind of variable stars are there? Well, there's eclipsing binaries. They wouldn't do this. They do the opposite of this. They're bright and then they dim briefly and then they come back. So it couldn't be eclipsing binaries. Well, what about Cepheids? Well, Cepheids go through a pulsation like this, okay? So they don't do this either. And most of the other kinds of stars that are variables are variations on the Cepheid theme. They're pulsating stars. There is one class of stars, though, that does do something like this. They are called flare stars, and they're normal, and then bloop, they get bright, and then they dim down again, and then they go back to normal. Flare stars. So we want to guard against getting fooled by flare stars. So what are flare stars? They're mostly red dwarfs that have deep convection zones and strong magnetic fields. And you can have solar flares on those that are way, way, way bigger than the solar flares that we see on our star. We're lucky we don't have a star like that, because the flares here can brighten the star by a factor of 10 or even 100. And if the sun did that, well, it would, sterilize the Earth. We would be like those cartoon figures, who are holding a dynamite stick, and then a moment later they're all black and smoking. Yeah, so that would be us. We don't want that. So we could look for flare stars. How do we check and make sure that our machos are machos and not flare stars? So here's how you do that. Flare stars are dim and red. But when they flare, the light that's coming off that flare is very hot. It's very blue. And so the color of the flare is going to be very blue. So what you do is you take not one picture every night, but 2 pictures every night. And you do one in a red filter, and you do one with a blue filter. Now, what does gravity do? What would a real macho do? What a real macho would do is it would bend all the light. It doesn't care what the wavelength is. It all follows the geodesics determined by general relativity around that gravitating object. And so what you would get is a uniform brightening in red and a uniform brightening in blue and green and any other color you can think of. A very clean, easy test to make sure what you're really seeing is a gravitational lensing event. So the Macho collaboration really did their homework and they figured it all out. And they were very successful in carrying out the mission. Here's another Macho. And they did see some Machos. What did they find? The project ran from 1994 to 1999. 6 years of data, 12 million LMC stars. How many Machos? 15, roughly. 15. But Rick, you said they were supposed to see hundreds and hundreds. Yeah. So what does that tell you? It tells you the dark matter is not Machos. Okay, but the story's not quite done yet. There's another group. Of course, they needed a name that could be just as catchy, because you need a catchy name if you're going to get funded, right? That's half of funding, is getting a catchy name. I'm joking, I think, but anyway, you do want people to remember you. So they said, well, let's use the bold stars of the Milky Way. I mean, we do have Bada's window. We do have a little region where we can see the outer bulge of the Milky Way. We can get lots and lots and lots and lots and lots and lots of stars on one CCD chip, more than the LMC people could. And because we're towards the center of the Milky Way, and because the dark matter from our rotation curves does seem to be denser in the middle of our galaxy, and of course it's pretty hard to imagine why it wouldn't, no matter what it is, be denser towards the middle of the galaxy, they expected a much higher event rate. And they had much higher sensitivity, and so they should see lots and lots of events. So they got funded too, but they needed a good name as well. So the Optical Gravitational Lensing Experiment. So if you could be Macho, you see, you could also be an ogler. Anyway, adolescent males, what are you going to do? Actually, they're a little older than adolescent, but they still got a little bit of that in them. But we all love that, right? Okay, so the Ogle experiment is actually still going on, or it was until, last I checked it was. 19 years of data, again, they confirm basically what the Macho collaboration found, and that is no, there's nowhere near enough events. They did see some, but not enough. So we have good confidence now. The dark matter is not Machos. There was a new study by Nakura et al. Came out just last year, and they've even been able to rule out low-mass so-called primordial black holes through gravitational lensing of stars in the Andromeda Galaxy. So we've ruled out all forms of ordinary matter, from atoms all the way up to elementary particles of, well, atoms are made of elementary particles. So let's say atoms glom together to make molecules. So you can rule those out with absorption lines as well. Dust. So now we're talking about little bits of hundreds or thousands of molecules glom together. And then up to rocks, and then up to asteroids and comets, and then up to planets. Planets are self-gravitating. The Macho collaboration would have found those. To dead stars, red dwarfs, white dwarfs, you name it. We've ruled out all forms of ordinary matter. We've gone up the size scale from the smallest to the biggest, and we've ruled them all out. They all have observational consequences, and we've checked it out.